Hey everyone. I hope everyone is staying safe and well as we learn from home. I'm going to do these videos for our class, Math 1101 for Middle Georgia State University. I know that we have already started section 4.1, but that was a long time ago, so I'm going to reiterate some things that we went over before spring break happened. I'm going to do these videos all in one take, sort of like how our class goes. You know, you show up, I show up, and then we just, do it. So here we go. As you can see, I've got a TI Smart View at home. There is a way for you guys to get a version of this for free from Texas Instruments for 6 months, and I will be posting that in D2L. I'll also post all these videos on D2L after they're done. I'm going to post them to YouTube if possible. Okay, so let's get her done. All right, so polynomials. I'm also writing with my finger here, so bear with me. So what's a polynomial? Definition. A polynomial function is of the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. Oops. And it goes like that all the way down to a sub 1 x to the 1 and a sub 0 x to the 0. Now, not all polynomials will be of this form immediately, but if you multiply them all out, you should get, and simplify them, they should look something like this, okay? So, for example, still trying to use this thing, my finger, it's hard. For example, you could have f of x equals, say, negative 3x to the 5th minus 7x squared plus 2, okay? And this right here is the important term. It's called the leading term with leading coefficient, in this case negative 3. So negative 3 is our a sub n here. And n is the degree. I didn't write that before, but degree is the highest power of x in a polynomial. So it equals 5 in this example. Okay, the 2 here is the constant coefficient, and it turns out that that's the y-intercept. Right? So a sub 0, or the coefficient in front of x to the 0, that's going to be our y-intercept for polynomial function written like that. There are other examples of polynomial functions, okay? Pretty much if you are trying to figure out if something is a polynomial, you look for the powers of x. Are they whole numbers and not negative? So this is not a polynomial, right? Square root of x minus 2. Or this is not a polynomial, x to the negative 2/3. Okay, neither of those are polynomials. Not polynomials. Okay, maybe another one that you might see that's not a polynomial is if there's an x in the denominator. So that would be a negative power of x if we were to write it out another way, perhaps. But at any rate, none of those are polynomials. So we need to be able to recognize what is a polynomial, right? So some tasks we need to practice. Recognize when something is a polynomial and not. And also, so recognize, let me try to write that better. Recognize polynomials. And what else? We need to be able to find their degree, leading coefficient, okay, because later on we're going to see that that will tell us about something called end behavior. Which we'll learn about in the next section. Okay? So, moving on to something, so those are things that we did in class already. And of course, you have lots of tools and content in Desire to Learn already for these sections. You go to the content browser in D2L and you can find all of the online class content. So this is just going to be, my lectures are going to be a supplement to that, and hopefully it will make it easier for you to find or understand those resources. All right, so one thing that's true about polynomials is that their graph, the graph of a polynomial, graph of a polynomial is smooth. Hey dude, it's super smooth. Okay, what does that mean? Well, it means you can't have any of these things. You can't have a vertical asymptote, a kink, a corner, a hole, or a jump discontinuity, or pretty much any other sort of bad thing about a graph, like the fact that the domain needs to be all real numbers if the function is a polynomial. Okay, so smooth means no kinks, corners. Sorry, this is not written very well, but I'm doing it with my finger. Kinks, corners, vertical asymptotes, or discontinuities of any type. So no holes or jumps, right? And the domain of a polynomial needs to be all real numbers. Okay? So, we know the following is not a polynomial. Right? Here's a graph of some function. It goes from there to there and stops. Okay? Not a polynomial. Because even though it looks smooth inside the domain is not all real numbers. Okay? Not only that, here's another one that's not a polynomial. That is not a polynomial. Even though the domain is all real numbers, it's got a corner. Okay? So these are not polynomials. But these are polynomials, perhaps. So got a really squiggly graph, but it's smooth, right? To draw the whole graph, I don't take my finger off the computer here, and I don't make any sharp turns. Okay, so here's another one we've seen before. There will be some these are polys. There will be some general shapes of graphs of polynomials that you will come to recognize. For example, ones like this. Okay, you've seen these before. Here's an example of a polynomial of degree 1. Here's one of degree 2. Right? A linear function is a degree 1 polynomial. A quadratic function that has a parabola as its graph has degree 2. Later we're going to learn about cubic ones that might have 2 turning points and quartic ones that could have 3 turning points. Okay, so here this would be, the degree would be 3, here the degree would be 4. Alright, last but not least for this video, this is going to be part 1 of section 4.1 here. I want to talk about local max and min. Also known as extrema or extreme values. Local max and min are turning points. So we did this a long time ago when we looked for the places where function was increasing or decreasing. Okay, these are just turning points. Okay, so if you look at my example here on the calculator, I found, first of all, I went y equals, and I put x cubed minus 8x plus 1. And I graphed it, and that's what it looks like. Okay, and if I wanted to find the local max or the local min, those are the turning points, right? So the local max would be this one. Local min is this one. To find it on the calculator, you go to second trace. Maximum would be a local max. Okay, so we move the cursor somewhere to the left of where it crosses, or where it makes a high point, then move somewhere to the right. Hit enter, bring it back. Boom, we get an example here of a turning point that, so here in this example, oops, let's make this black. Example, f of x is x cubed minus 8x plus 1, I think. Was that it? Yes. And then we wanted to find local max. To do that, we use second trace. Second trace 3. Oops. Quit. Second trace 4 for maximum. Move the cursor somewhere to the left, then to the right, as I said, and then guess. Second trace 4. And we get that this one is about negative 1.639.7. Now, the actual local max is the y value. Okay, but on my math lab, it might ask for the local max or local min as a point on the graph, and then you would give both coordinates for the turning point. Okay, so that's it for local max. You can practice that some more. Absolute max is another thing that you'll have to do. Those are the absolute highest y value or lowest y value of a function, a polynomial function in this case. So for example, this one here has none. No absolute max and min, max or min. Because it goes up to infinity, there's no highest point, and down to negative infinity, there's no lowest point. Okay? On the other hand, this does have an absolute max, but no absolute min. Okay, so the y value of this point right there is going to be our absolute max. Absolute max here, but no absolute min. Okay, so if you have any questions about this video, post them on D2L or email me through the D2L email D2L email apparatus app, and or on the discussion forums that I set up in D2L for you for that purpose. Okay? Thanks a lot.